When humanity began sending spacecraft to the planets, the order in which we visited them was strange. Venus came first, in 1962, followed by Mars in 1965, and then Jupiter in 1973, a world more than 360 million miles away. Mercury, our innermost neighbor, did not get a visitor until 1974, and that visitor never stopped. It flew past, photographed less than half the surface, and left. And then, for the next 30 years, nothing followed it at all. In that time, we returned to Jupiter again and again. We sent missions to Saturn, to Uranus, to Neptune, to comets and asteroids far out in the cold. And Mercury, which is on average the closest planet to Earth of any in the solar system, closer on average than Venus or Mars, sat unvisited. It was not because Mercury was boring. It was because Mercury turned out to be one of the hardest places in the entire solar system to reach. Reaching it and stopping there requires more energy than leaving the solar system altogether. And when we finally did get there, when a spacecraft called Messenger settled into orbit in 2011, after 6.5 years and nearly 5 billion miles of traveling, it confirmed something that should have been impossible on a planet where the surface reaches 800 degrees Fahrenheit. It had found water ice, frozen solid and sitting there in the permanent dark. To understand why Mercury was skipped for 3 decades, you have to understand a piece of orbital mechanics that works the opposite way to intuition. Traveling toward the sun sounds easy. You are falling after all, and the sun's gravity does the work for you. And that part is true. A spacecraft aimed at Mercury accelerates the entire way in, gathering speed relentlessly as it drops deeper into the sun's gravity well. The problem comes at the other end, when the spacecraft actually has to arrive. Mercury moves around the sun at about 30 miles every second, roughly 60% faster than Earth does. To orbit a planet, you must match its velocity almost exactly, and a spacecraft falling toward the sun arrives traveling far faster than that. Shedding all that excess speed requires an enormous amount of fuel, and fuel is weight. And weight is the one thing spacecraft designers guard most jealously. Every pound of propellant is a pound of scientific instruments you cannot carry. Run the numbers with 1970s and 1980s propulsion, and the answer came back the same every time. A spacecraft carrying enough fuel to stop at Mercury would have almost no room left for anything worth sending it there to do. Mercury was not being ignored so much as it was, by the standards of the technology available, effectively unreachable. While Mercury sat unvisited, the case for going there quietly got stronger, and it came from an unexpected direction. In 1991, astronomers using the Arecibo radio telescope in Puerto Rico bounced radar signals off Mercury and studied what came back. Most of the planet reflected exactly the way bare rock should. But near both poles, small patches returned signals that were unusually bright, reflecting radio waves in a manner characteristic of ice rather than stone. It was a genuinely startling result. Mercury is the closest planet to the sun, with daytime temperatures hot enough to melt lead, and radar was suggesting there was frozen water sitting on it. But radar alone could not close the case. Ice was one possible explanation for that signature, and it was not the only one. Sulfur compounds could produce something similar, and so could certain kinds of rough surface texture. To distinguish between them, scientists needed to know exactly what terrain those bright patches were sitting on. And they could not find out, because the only spacecraft ever to visit Mercury had mapped less than half of it. There was no complete map of the poles to compare against, so the observation sat there, unresolved. a tantalizing signal from the hottest planet in the solar system, pointing at something that seemed to contradict everything about the place. The strange thing is that the physics allowing ice on Mercury is not exotic at all. It comes down to two ordinary facts that happen to combine into something extraordinary. The first is Mercury's tilt. Earth leans over on its axis by about 23 degrees, which is what gives us seasons and which means our poles spend part of the year tipped toward the sun. Mercury leans by less than 1 degree. It stands almost perfectly upright, and its poles never tip toward sunlight at any point in its orbit, ever. The second is that Mercury has essentially no atmosphere. On Earth, air scatters light into shadows and carries heat from warm places to cold ones. Step into the shade here and it is cooler, not lethal. On Mercury, there is nothing at all to do that work, and so a shadow there is absolute. Put those two facts together and something remarkable follows. There are craters near Mercury's poles, deep enough and angled just so, whose floors have never received a single photon of direct sunlight. Not this year, not last century, not since the crater was carved. And with no air to warm them from elsewhere, those floors grow colder than almost anywhere else in the solar system. Colder than the surface of Pluto, which orbits nearly 40 times further from the sun. They are called cold traps, and they sit a few feet away from ground hot enough to melt lead, separated by nothing but a crater wall and a permanent shadow. The reason Mercury stayed unreachable was never a failure of imagination about why to go, but a simple matter of arithmetic. And in 1985, someone did that arithmetic differently. Chen-wan Yen was a trajectory specialist at the Jet Propulsion Laboratory, a physicist trained at MIT who had joined JPL in 1973 and spent her career on the problem of getting spacecraft to difficult places using as little propellant as possible. She had already designed the trajectory that took Magellan to Venus, and she would go on to design routes for Cassini and Stardust. What she worked out for Mercury required no new technology at all. It required accepting a much longer road. Rather than flying to Mercury, a spacecraft would loop repeatedly around the sun, passing close to planets along the way. And each of those encounters would be arranged not to speed it up, as gravity assists usually are, but to slow it down. By passing a planet on the correct side, a spacecraft gives up a small amount of orbital energy to that planet and comes away traveling slower relative to the sun. A single planet cannot shed nearly enough speed on its own, but 6 separate encounters, arranged carefully across years, can. Her solution called for a flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself, spread across years, before the spacecraft would finally be moving slowly enough for its engine to capture it on the 4th approach. It meant flying past the destination 3 separate times without stopping. The full route would cover nearly 5 billion miles to reach a planet whose closest approach to Earth is 48 million. Nobody acted on it immediately, but by the late 1990s, with Mercury's polar radar signals still unexplained, NASA revisited the idea, found it sound, and built a mission around it. Messenger launched from Cape Canaveral on the 3rd of August, 2004. The name stood for Mercury Surface, Space Environment, Geochemistry and Ranging. And by the standards of flagship missions, it was small, weighing about 2,400 pounds at launch. More than half of that was propellant. The most visible feature of the spacecraft was not an instrument at all, but a shade. At Mercury, sunlight is roughly 10 times more intense than it is at Earth. So Messenger carried a sheet of heat-resistant ceramic cloth held permanently between itself and the sun. The front of that shade would endure temperatures in the hundreds of degrees, while the instrument sitting in its shadow, inches behind, stayed near room temperature. The spacecraft crossed the inner solar system hiding behind a parasol. It also used a subtler trick. Sunlight itself exerts a faint physical pressure on anything it strikes. And by carefully angling its solar panels, the mission team could turn that pressure into a gentle brake. The force involved is minuscule, but applied continuously across 6.5 years, it added up to real savings in propellant. And propellant was the entire reason Mercury had been out of reach in the first place. The journey was not without a moment of genuine fear. During the third Mercury flyby in 2009, the spacecraft passed into Mercury's shadow and had to run on batteries alone for 18 minutes. Something in the power management software was not configured correctly, and Messenger dropped into safe mode, shutting down its science operations to protect itself. For 7 hours, the team on Earth could do nothing but wait. The spacecraft eventually recovered on its own once the solar panels recharged the battery and the computer reset. But that flyby was one of the encounters the entire trajectory depended on, and it happened 5 years into a 6.5-year journey. On the 18th of March, 2011, Messenger fired its main engine and slipped into orbit around Mercury. It was the first spacecraft in history to do so. Even in orbit, Messenger could not simply sit and stare. Mercury itself is a problem, because a planet that hot radiates its own heat back into space, and a spacecraft flying low over it is being cooked from below as well as from the side. So the orbit was made deliberately lopsided, swinging in to within about 120 miles of the surface and then back out to 9,000 every 12 hours, so the spacecraft could cool down between passes. It observed in bursts and then retreated. The case for ice was not built on a single photograph. It was built on 3 independent instruments agreeing with each other. The first was a neutron spectrometer. Hydrogen has a distinctive effect on neutrons produced when cosmic rays strike a planet's surface. And water is one of the most hydrogen-rich substances there is. As Messenger passed over the North Pole, the instrument detected exactly that hydrogen signature, concentrated precisely over the permanently shadowed craters. The second was a laser altimeter, built to measure the shape of the surface by timing laser pulses bounced off it. As a byproduct, it also measured how reflective the ground was, and in the coldest of the shadowed craters, the floors reflected exactly as bright ice should. The third was not an observation, but a calculation. Using the real terrain that Messenger had now mapped in detail, researchers modeled how cold each crater floor ought to be, accounting for heat radiated from sunlit walls above and conducted through the rock. The places the model predicted would be coldest turned out to be the same places the radar was brightest and the hydrogen strongest. On the 29th of November, 2012, the results were published in 3 papers at once. 21 years after Arecibo saw something strange, the case was closed. There is water ice on Mercury, in permanent shadow near both poles, in deposits running several feet thick, and in the deepest cold traps far deeper still. The closer Messenger looked, the stranger the picture became. In the very coldest craters, the ice lay exposed at the surface. But across most of the deposits, it was buried beneath a thin layer of unusually dark material. And that material was not ordinary dust. Its properties matched organic compounds, the carbon-rich molecules that form the chemical foundation of biology. The prevailing interpretation is that this dark crust acts as insulation, shielding the ice beneath it from evaporating into space, even in places slightly too warm for bare ice to survive. Which raises the question of where any of it came from, because none of it was made on Mercury. The leading answer is that comets and water-rich asteroids have been striking the inner solar system for more than 4 billion years, and they carry both water and organic material with them. On almost all of Mercury, anything delivered that way would vaporize instantly. But a fraction of that vapor, drifting across the planet, eventually wanders into one of the permanently shadowed craters, freezes solid the moment it touches the floor, and never leaves. 4 billion years of bombardment slowly filtered down into a handful of frozen deposits at the poles. If that is right, then those craters are not merely curious, they are an archive. The same combination of water and carbon chemistry that rained onto the early Earth, and which may have set the stage for life here, has been sitting preserved in the dark on Mercury for longer than complex life has existed on our planet. The world closest to the Sun, too hot and too small to ever have hosted life of its own, may be quietly holding a sample of the ingredients. One puzzle from all this remains unsolved. Only about half of the permanently shadowed ground at each pole shows the bright, icy signature. The rest sits in the same darkness, at similar temperatures, and shows nothing at all. Some of those craters may simply never have received much water. Others may have lost theirs, or have it mixed so thoroughly into the regolith, or buried so deep that our instruments cannot see it. Nobody has yet worked out which of those explanations is the right one. Messenger was designed to operate at Mercury for a single year, and it lasted 4. Mission planners had hoped it might return around 1,000 photographs across its lifetime. It returned more than 250,000, along with over 10 terabytes of data, and gave us the first complete map of a planet that had been half unknown for 30 years. But it launched with a finite amount of propellant, and out there is no refueling. By late 2014, the tanks were nearly dry, and the spacecraft's orbit was decaying toward the surface. Engineers bought extra weeks by venting pressurized helium, a gas carried only to push fuel through the lines, never intended to serve as propellant at all. They were using the plumbing as an engine. On the 30th of April, 2015, that ran out too. With nothing left to raise its orbit, Messenger fell and struck Mercury's surface at roughly 8,700 miles per hour, carving a fresh crater about 50 feet across. The impact happened on the far side of the planet, out of contact. There was no final image and no last transmission. The spacecraft went around the horizon on one more orbit and simply never came back. It became a permanent feature of the world it had spent 11 years trying to reach. What Messenger left behind was an inversion of everything Mercury was supposed to be. The planet closest to the Sun, the one place where frozen water sounds like a contradiction, has been holding on to it the entire time, protected by nothing more than the angle of a crater wall and the fact that Mercury barely tilts as it spins. There is something worth sitting with in that. The very thing that makes Mercury so extreme, its closeness to the Sun, is also what makes its shadows so absolute. The same geometry that creates the furnace creates the freezer. And Mercury is no longer being ignored. A joint European and Japanese mission called BepiColombo launched in 2018, following its own long looping road through the inner solar system. And after nearly 8 years of falling toward the Sun, it is now in its final approach. It carries 2 separate orbiters that will split apart on arrival, 16 instruments between them, and it is scheduled to enter orbit around Mercury on the 21st of November, 2026. It will be only the second spacecraft in history to do so. As for what is hiding in the half of Mercury's cold traps that show no ice at all, that is a story for another day.